Welcome to the Cosmic Pie Podcast, Season 3, Episode 30. I'm your host, Wayne Barkhouse.
And I'm Robert Moore.
We are broadcasting live as opposed to dead from the campus of the University of North Dakota here in Grand Forks. Before we start, what we always like to say at the beginning is a disclaimer.
There's a disclaimer, but I think I'll let you handle that one this time.
So anything that any of us says, Robert and I, or our special guest, which Robert will introduce here in a moment, is our own personal opinions, not necessarily opinions of the University of North Dakota, the College of Arts and Sciences, the Department of Physics and Astrophysics, the state government, the federal government, the planet Earth, even the universe. It's just us.
It's just
so
us.
Blame us if you find something you don't like.
Yep.
The other thing is we do have a live chat feature that is running, so if you have any questions or comments, you can send that to us during the podcast and we'll answer them. And for those of you who only watch this as a recording later on in YouTube or on Spotify, if you actually tune in live, you can actually ask us things that we could ask questions of our guests when we have guests, or just Robert and I when it's just us.
Or we might try.
We'll try. Okay, Robert,
All right.
do the honors.
All right. Well, with us today is Mr. Scott Harris. He works with the University of Georgia. He is a planetary scientist, as I recall. I've worked with him a good bit at my last little geek fest that we mentioned last week, Dragon Con. He is bringing out some solar telescopes for us to use at that occasion. And basically, he's also worked with Fernbank Science Center in downtown Atlanta and with a planetarium in Charleston, South Carolina. So he's done a lot of work. He works a lot with meteorites and, in fact, is the gentleman responsible for curating, I guess would be the term, the one that recently fell on a house in Georgia. So, Scott, I'll let you finish your introduction.
Well, thanks, Robert. I wear lots of hats and have over the years. I'm a very firm fixture in the impact geology community. I've been doing planetary science and planetary geology for most of my life at this point, having been a mentee of Ron Greeley, an eminent planetary geologist at Arizona State for many years. And back then, as I was telling you earlier, I actually worked on volcanoes. And but then life had some interesting little curves, and I ended up having the good fortune of being in the field with Eugene Shoemaker at Upheaval Dome in Utah back in 1997, and just almost if somehow divine providence, a few months later, or actually not a few months, a few weeks later, unfortunately, Gene was dead in Australia in a car accident, and my life kind of took a turn toward impacts, and that's all I've done ever since. So working on initially with material ejected from the Chesapeake Bay impact in Virginia 35.5 million years ago, and then ultimately working with Pete Schultz at Brown University for many years now, concentrating primarily on impact deposits in South America. And so I deal mostly with the actual collisions and the products of those collisions and what happens to Earth in those collisions. That's why this recent fall here in Georgia, people were interested in the rock, and I ended up doing analyses of the rock. But I was most interested in the dynamics of this thing going through a house. I mean, that's really, even though it's small, yes, I wanted to know what was going on with it going through that house, and it turns out to be quite a story.
Okay. I never thought about that being interesting. I got to admit, it's the end result, the product that's interesting. But no, you're right. How it penetrates the house, what it goes through, how it damages it, how it projects outward, and all that would be quite interesting, actually.
Well, as I always tell people, we're in this business in impact science for being the worst kind of actuarials. Right, we're telling you what the risk. We're trying to use the geologic past and the present to tell you what the risk of utter doom is for the future.
Certain
no
doom.
No sort of skirting around the edges there. What's your chance of death? And just catastrophic death for everybody. But also we're worried about the small ones. And I don't know if you know this, but yesterday, as I often call it, is Carankus Day. 18 years ago, September 15th, 2007, was the last time we actually had an impactor hit Earth and make a shock excavated crater down in Peru, and I was very fortunate to be on the first team to work on that. So it was really there's really some real scientific interest with this one that happened to fall kind of in my backyard here in Georgia, to see something really tiny that broke up in the atmosphere and then do some significant damage on the ground, even though the one in Caracas was something that made a 50 to 60 foot crater. This was just a tiny thing here in Georgia back in June, but still the dynamics of it, understanding the speed and everything, is really, they're important things to be learned there from a planetary protection standpoint.
Right.
Now, Scott, was there multiple pieces of this fragment that came down in June found, or just the one piece because it went through someone's house? And
No, there are multiple pieces, and just like this is going back to what I just said about Caracas. We know that object was a couple, basically 3 to 6 feet across back in 2007, and broke up twice. We have infrasound data that said it broke up twice in flight, but still material stayed close enough together that it hit as a single mass and was able to excavate a large crater.
Oh.
So when somebody says, hey, we've got these tiny things, but still traveling at, possibly cosmic velocity, that gets my attention, no matter whether it's in my backyard or not. And so what it looks like happened here was that you had a pretty normal meteor coming through, maybe again 3-4 feet across, and it breaks up maybe once or twice, as many of these ordinary chondrites will do. And but in this case, while it didn't stay together like in Caracas and put a hole in the ground, it did have a very pretty confined ellipse of the strewn field, and it really looks like, from what I know right now, and there may be some other information out there, some of the pieces that were collected were sent off to colleagues at actually my undergraduate alma mater, as I mentioned, Arizona State, and those got sent before I was able to get back and look at the house and everything, and I had sort of exclusive access to the material that hit the house and was able to make the measurements and everything. But it looks like that basically what happened is this thing, had at least one catastrophic breakup at altitude, and the larger, more competent pieces then sort of go flying to the outside, and they came down, and then in the middle of the ellipse are just tiny little granules. So out on the outside, we have things, from what we estimate the original size of the one that went through the house would have been, maybe about the size of a large cherry tomato, small walnut with about a mass of 70 grams, up to things like this one that was found about a mile away that from that site on the other side of the ellipse that's about 200 grams. There are a number of those, not a lot, but a number of them around, literally forming the edge of the ellipse. In the middle were just sort of like little pea gravel.
Huh.
Now, when an object comes in like that, does it matter, like the path length through the atmosphere, in terms of how many episodes of major breakup that it will experience?
I'm sure it does, but I think more important is, what's the material properties of that object, and not every, even ordinary chondrite, is made the same. Sometimes when you get these things, even in this one, when some of my colleagues looked at it and said, oh, this is a L6, and I said, well, the piece I have is really a L5 or L5-6, and this piece that someone just as a result of media attention, alerted me to. As you look at this one, they're actually visible chondrules that you can see in hand sample. So it may be even a slightly less metamorphic grade, maybe a little more strength, a little bit more competency, that would make sense at staying together as that larger mass. So even like Caracas I mentioned, when we looked at that, that object was already heavily fractured before it even got to Earth's atmosphere. So,
okay.
I think, that's one of the reasons we're interested in these small bodies. That tells us something about the materials and material strength that becomes relevant to, hey, are we going to have to go hit, one of its larger cousins with a kinetic impactor at some point to protect the planet? If you hit something that's already busted up and fractured, well, okay, now you've got buckshot. It's the old problem of you don't blow them up because you're going to have buckshot coming at you. Well, you could do the same thing with kinetic impactor if these things are really friable. And so, I think the material properties really matter more than the angles and even the entry velocities.
Right, so that would affect, if you like, I mean, I'm not a geologist, so I'll say that, but I mean, something I think about is like porosity of the material itself, and if that's loosely, came together at an earlier time, maybe it was more of a solid object or from a parent object that then, comes together, then impacts the Earth, then that tends to be, operate differently than if it's some like an iron meteorite that comes in that's a solid body.
Yeah.
Yeah, and I think you're right there too, in that we think about a lot of times as these coming in, and we see the data, or we see them visibly, or see the infrasound data saying, hey, that broke up. But what is the nature of that breakup? Is that breaking up something that was coming in as a few meters of solid material, or was it already just loosely bound together? And so is that breakup really representing it just sort of, just immediately responding to the dynamic stress? And maybe even some of those that you think, well, gee, if this is already a little miniature rubble pile, it's just going to fly apart. That may actually be opposite. It may be that some of those that are already kind of bound loosely have an easier time getting some large pieces. One of the things we found with Corangus is you get a large piece that's out in front, creating a bow shock in the atmosphere.
Right.
That shock wave can actually gather smaller pieces together and keep them bound together in flight. And so, those are some of the physical parameters, I said, maybe even relevant to having larger things that come into our atmosphere that we need to worry about.
Now, could you model something like that in the simulation?
I sort of, I'm really on the material side of the geology,
Right.
so don't ask me to do it. But yeah, I mean, some of the people I work with, say with some of the national labs and such, that look, a lot of our major dynamics experts, really their day job is, while they're trained in impacts and impact physics, hypervelocity physics, their day jobs are at national labs working on military applications.
Right.
And they sort of moonlight over here with the geology side. But yeah, so through them, yes, I mean, they try. But it's a challenge. I mean, you start talking about those larger rubble piles that are out in orbit around the sun, and we encounter those, and what would we do about them? Those become extremely non-trivial problems.
Very quickly. Yeah.
Yeah.
I've often commented to people before that start getting onto this discussion and talk about how, we saw one come in, just blow it up with a nuke. And it's like, okay, do you want to be hit by a rifle or a shotgun? Because that's the choice you just made.
And then you have this weird thing like happened here back in June. I mean, where this family's house was just absolutely, I kind of compare it to being shot by a super 50 caliber rifle.
Right.
And clean shot through the house. And if he had been 14 feet in the wrong direction, we'd be having a very different discussion about this meteorite.
Right.
Now, how far down in the house did that penetrate? Right down into the basement?
Well, there was no basement. It was a concrete slab. And so that's one of the regrets is like, boy, I wish that had a basement just to see how far it'd go.
Yeah.
But it clean shot the house. What I mean by that is when colleagues knew that I was going to be able to go to the house for the first time and investigate this, they said, okay, you've got to go in the attic. There has to be material that, bounced off the roof. There has to be material in the gutters. There has to be material in the attic. There's got to be this little tiny amount of material that the civil authorities showed on TV right off the bat. That can't be it to create the damage that we're seeing to this house. And so that was a priority when I went in, and say, okay, let's go to the attic and look. And the homeowner had not even thought about that yet. And he was awful glad for a sort of interesting reason that I did, because he'd been working with the insurance company, hey, repair my ceiling, repair my roof, repair my floor, and never dawned on him that he had an air duct, big fluffy, aluminum sheet air duct. It went through one side of it and out the other. I mean, just as somebody had taken a rifle to it. And when you looked at it and the insulation and everything, looked at the hole, looked at the entry hole in the roof, these were absolutely clean. There was no debris from this rock at all.
Wow.
It did not fragment at all until it hit the floor, and when it hit the floor, it put an actual about a almost 2 inch little crater. I mean, there's even like directionality that you see in the crater, and this beautiful fracture pattern and everything in this synthetic laminate material. And then there was at the bottom of the laminate, there's a little bit of a soft material, and then you've got the concrete slab. And when it hit that, it rebounded off of, still traveling incredibly fast. It had to have been rebounded off of that. The front, I estimate about the front third of this, small walnut just disintegrated to dust. The back, just as if this were a larger impactor, spalls off. And some of the spall fragments, of course, don't have the opportunity to detach enough that they then don't slam into the floor. So when they hit, they still had enough force that some rebounded more than 5 to 6 feet in the air, landing on the refrigerator and mantle, and some bounding 25 or more feet down hallways into other rooms.
Wow.
I mean, I just regret that the guy whose house this was home. He was on a Zoom call, no video running, no sound being recorded.
Wow.
It's like, could we just go back in time, even with it being in the room behind you? I want to see the dust fly in the distance. I want to hear it.
Right.
But no such luck on this.
So what did he describe the sound though, right? Because he heard it, obviously, right?
He heard it, and he happened to be in a, like I said, in a meeting where he had on a noise canceling headset.
Right.
And he said even with that, it sounded like, just incredibly loud gunfire. And what I speculate right now, based on the information I have, I really believe that this thing went subsonic pretty much at his floor. So 14 feet away, he would have simultaneously heard the collision with the roof, the collision with the, probably muffled by hitting the actual ceiling board, but certainly heard the roof, the floor, and his own little personal sonic boom somewhere there in the middle. But of course, at that distance, you wouldn't be able to distinguish those, so it just all that amplified together. It was, he describes it as quite a sound, and I can only imagine that it must have been. And maybe he's fortunate that he had on those headsets, given how close he was. But still, his, immediately after the sound, he had a little tiny fragment, little granule, come bounding into the room behind him.
Wow.
So did he piece it together, what it was, or did it take a while?
Well, turns out that he actually is a scientist.
Okay.
And very, very, very smart guy, and I think he pretty quickly understood what was going on. But he's also, I've described him, and I'm kind of working with him. He might actually be doing some interviews down the line here in the future. He's got he's kind of a private guy. He's has a young family, and he really wanted to maintain that privacy, and we all can understand that.
Yeah.
But he also is an insanely calm man. I mean, I've described him as just being someone that I could imagine, detonating a bomb next to, and you'd have to check his pulse to make sure that you'd even notice. I can't you just can't overstate how calm a gentleman this is. And he had this really he's also a spiritual man. And he literally, I don't think he'd be upset with me for describing, what he told me, which is he had actually kind of had some prayers and asked for some signs on some things the previous night. So for that initial moment, it was there was a spiritual moment there of, well, I guess I got I have never asked him what the question was, but it clearly got an answer. And then the next thing was, his attention turned to, this happened, right at the end of the lunch hour, and his wife and kids were out at the store getting lunch, and they were due back home in about 15 minutes. And he describes it as, I have a hole in my ceiling, and my wife's going to be home soon. What do I do?
How am I going to explain this?
You literally just became part of science history here in a pretty dramatic way, and your thought is I've got to make sure my wife's okay with the hole in the ceiling, and we got to get that plugged up with the so the kids don't have rain coming in on them. And great dad, right? I mean, priorities where they need to be.
Well, that's one of the questions someone would ask. An obvious one is, will insurance cover everything?
So they have been. My understanding is finally asked him a couple days ago that they've been really good about it. Other colleagues that I've talked to who've been working with people in similar situations. We always hear insurance companies sort of talking about those acts of God and what they will and won't cover, and so you might be a little pessimistic. But the reality is, as I've described it, is like, look, a lot of those acts of God are things that, while they are rare to happen to an individual, you're unlikely to experiencing them yourself. Even in a given thunderstorm, a given hurricane, or whatever, even a given earthquake. While you personally don't have a large chance of something happening, there is a large chance of something happening to a lot of people in that area.
Yeah.
Right.
And that's very different than, okay, a meteor's falling out of the sky. There, your real odds are very low, and they kind of get that and really don't give anybody grief about it.
Okay.
Yeah, that makes sense. Now, how did he get a hold of you? So who did he if that happened to me and I wasn't a scientist, I'd be wanting, do you go to the old days, the yellow pages of the phone book? Right?
Well, here in Georgia for quite some time, myself and one of my friends and colleagues for a long time, actually my predecessor in a sense at Fernbank Science Center when I used to work for them, Ed Alban, who's also both a ASU and UGA alum. He and I we're kind of the go-to guys here if anything falls out of space. But how often do you expect something to literally fall out of space? But I work on impacts. Ed is he's a planetary geologist too, but a little bit more engaged with the fireball monitoring. He has 2 AMS cameras that he has set up. Some of the images, best images. He had one AMS camera, all sky camera that was, just literal miles from ground zero for this. So he does a little bit more of the astronomy side of it, and people kind of know who he is with AMS and with and Meteorological Society. And people generally know me too. I'm the president of the Atlanta Geological Society. I'm out there, talking about impacts and things all the time. While most of my research work is, outside this continent, we're actually been working for a long time on a likely large impact structure here in the southeast. So, people do know us in that regard, but we are sort of the go-to people and somewhat self-anointed in that case. I mean, we're this is not a region with a whole lot of planetary geologists around. There are more now than there used to be. UGA has some fabulous people with Chris Klimchek, who does structural planetary geology. There are some other people now, some students getting interested in meteorites from a mineral standpoint and understanding, say, weathering on Mars and space weathering on the moon. So it's a growing thing, but we're kind of been the materials guys around here for a while. So the last one we had actually before this, that's sort of said, you're in a state, even a large state, and you're like, how often do you really need to be called upon for this, right? Well, we've actually had a number of these events in the last just 16 years. So these things happen, and we kind of get the, we'd get the call and say, hey, can you look at this? Can you classify this? Whatever. With this one, I got alerted I was actually on a trip with my daughter out west. I think I was on my way. We weren't really there to look particularly at any given impact or anything, but I think I was somewhere around, ironically, the Beaverhead impact structure that's partly in Montana and partly in Idaho, when all of a sudden somebody sends me a Facebook message from here saying there's just a fireball just came over our heads, basically. And within 20 minutes or so, news stories were out. The information about that this material was being handed over to the sort of civil defense authorities, emergency management folks here in one of the local counties. So I gave them a call, and they acted rather relieved to hear from me, because it was like, yeah, we don't know what to do with this. So, and they were also, again, the gentleman whose house got hit, being very concerned about his privacy. They didn't want to, reporters were calling. There was a lot of attention, and so to have somebody sort of kind of handle the questions and everything, and sort of say, look, we're gonna, like, it was over a week it took me to get back home and get there to the house, but everybody was very patient about it, and it was great getting there and being able to really go in and see it for the first time from a scientific eye. And the homeowner, being a scientist, was very helpful in making measurements and doing things that data that we do need. And one of the coolest things I think that he did was we were able to get a large piece of rebar and put all the way through all the holes, so we could actually measure the actual angle and the azimuth of that object. And one of the reasons I'm very convinced that this was still traveling at very high velocities and maintained a lot of its horizontal momentum is the azimuth. Not just the angle is not completely vertical. Most of the time when you have objects come in and go into free fall, they just come, yes, they're on a parabolic arc, but they more or less, by the time they hit a house, are straight down.
Right.
This one's almost straight down, but it is off a little bit. It's a couple degrees shy of vertical. But more importantly, when you put the rod all the way through, the azimuth of that, trajectory was the same azimuth as the flight of the original object on all the NASA records.
Oh yeah.
So I think that piece actually was really never left trajectory. When the breakups happened, it stayed out in the lead and maintained a lot of the horizontal velocity, and also probably got a little bit of a kick forward from the last breakup event.
Now, can you work backwards on the trajectory to try to figure out what was the parent object, if possible?
I think some of the NASA guys already have, and I do not remember what that is right off the top of my head right now.
Right.
But what its orbit looked like. But as far as what the original parent body was, that comes from the classification, or at least the suggestion on this being an L ordinary chondrite. As best we know, L's, or at least most L's, come from a group that is still represented out in the main belt. There's a group of objects that, as I call them, the astro machinist, have run Kepler's laws in reverse, as you might say, and came to the conclusion that there's this group that broke apart about 470 million years ago. And we think most L's come from that event. So the smaller pieces that got cast out from that collision or breakup, I mean, you got different possibilities, right? It could have gotten hit by something else,
right? Or
it could have just unfortunately got itself into a bad situation with Jupiter in some resonance and catastrophically split. But the debris from that is represented mightily in the meteorite record. It's the second most common thing to hit us, and that not only goes down to objects that are anything from dust up to meter size that are collected as meteorites. There also L chondrites are represented pretty well in the large impact structure geochemical record. So when that breakup occurred, there were, at least a number of objects that got into Earth-crossing orbits that are on the, were on the scale of, 1, 2, 3 kilometers across. And, but the big boys, the ones that are still 100 kilometers across, are still, fairly close together, happily traveling around back there in the, back out in the main belt, and presumably there they will stay until something else catastrophic happens. But that, if you let me, the geology of that is really fascinating, because there is a quarry in southern Sweden back that covers rocks around that time of 470 million years ago, and in the wall of this quarry, representing millions of years of time, in that quarry, I think the current count is over 100 fossil meteorites. They're not all laid out on one horizon.
Right.
They're over a few million years. So the flux of those objects hitting, and these are all been tied to the that L chondrite breakup. It had to be, go outside there for any day on a million years and treat yourself to quite a life spectacle, I assume.
Okay, so that's not location specific. You're talking about bombardment of the Earth's surface in general.
Yeah. I mean, unless there was some mystical reason for that patch of Sweden to be picked on, you have to assume that flux is happening all over the Earth and all over the Moon too. Imagine it getting pelted, so you just see little, perhaps even luminous flashes on the Moon throughout that time. And the other fascination with L chondrites in this event is there is one of those fossil meteorites that is not an L. And it's actually some material that, at least some of the initial work that was done showed that it is a rather exotic material that could be something that came from deeper in the solar system. So maybe that is the offending object, a piece of the offending ammunition that caused the initial breakup, and then it kind of followed the rest of them into the inner solar system and came to roost here.
Now, is there any other location on the Earth that will allow us to probe back to those sort of times to see any remnants there, and should match up with what you see in Sweden?
There hasn't been quite the extraordinary find of that quarry, but trying to locate, even though there are plenty of Ordovician sediments out there, trying to find that exact little moment in time on the Earth that's another matter. But I've in my pure geology hat, I've been out in Ordovician sediments in the eastern North America, and I remember before this became news years ago, I remember a lot of things that were claimed to be drop stones that were in the Ordovician. They thought there was a big glaciation, and you have a lot of these sort of rusty looking rocks that are in these very quiet water limestones and dolostones. And so there are many places I've personally seen, I'd love to go back to, and it's like, is that rusty rock really a drop stone, or is that from a glacier, or is that just dropped straight out of the sky?
Right.
In fact, that's one of the major methods or techniques we use in Antarctica, right? You go along Antarctica where it's all ice, and if you see any rock, that's completely out of the norm, obviously, so it must have came from above. So clearly that's a major area to go to look for meteorites.
Yep.
Yeah, so any Ordovician stratigraphers out there, I always try to encourage them. I'm like, see any rusty rocks, don't assume they're just,
drop stones.
Nothing to look at.
I guess what I was thinking about is like, the iridium find, tied up with the extinction of the dinosaurs, 67 or 66 million years ago, depending on who you talk to.
Right.
And that one of the things out of that is the fact that was spread globally, right? It's not just in one isolated area, which we'd expect of that kind of situation. That's kind of what I was aiming for, if there was any evidence.
Yeah,
like that.
and so one of the things that I don't know, maybe forgetting, but if there's an iridium anomaly anyone's found there, but one of the things that one of the Scandinavian geologist, very good geochemist, Birger Smith, has done is he's looked for, because he knows they're in these grains, or he knows they're in these pieces. These pieces are very decayed, right? So it's not like going up and grabbing the rock like I showed you earlier. I mean, this is decomposed as clay at this point. But little grains of iron chrome oxides, chromite, are in those that have signatures of the impact, or isotopic signatures. And so
Right.
he's, I think, had some success in chasing those around, because you may not be able to find the exact, horizon like with uridium, but you're not looking for an exact horizon. You're looking for a bigger period of time for this bombardment. And I think he has had some success in being able to find some Ordovician sediments where there's an increase in the total amount of these extraterrestrial chromite grains.
Okay.
Right. Now with the proliferation, I guess, or whatever, everybody is buying ring cameras or similar devices. Does that help in your work in the sense that, maybe people see things that otherwise they would have missed and can point, hey, with all the triangulation, if you like, of these ring cameras, this is pointing to a general area where there might have been a surviving meteorite to go look for things like that?
That's it's important to the people who make those calculations for the trajectory, trying to track back, what the initial orbit of the fragment was before it encountered the top of Earth's atmosphere. But I tell you, more than anything, the technology that has allowed more information, more precise information to be gathered about trajectory, and also led to more objects, even when fireballs occur, and more recovery of material, because they obviously, most do not hit houses, so it's easy. Our Doppler radar.
Okay.
Even local weather stations and such that have their Dopplers running, some of the colleagues with NASA, can access those pretty quickly along with their own instruments, and that not only gives you very good information about what these objects, and our weather satellites too, the GOES satellites, and seeing flashes on the atmosphere that look like lightning strikes. Those data have really helped being able to refine very quickly what the trajectories were, where these were coming from. But the Doppler, more than anything, leads to you knowing approximate mass of material and its proximity to the ground. And so being able to have these ellipses of, basically heat maps of areas to go and look, and with expectation that we know how much mass should be there. I think you really revolutionized the meteorite hunting operations for the collectors and for the scientists.
Now, just before you hit that, does the Doppler give you enough resolution in terms of that you can calculate some motion of the object?
The ones I've seen, I certainly think that you can. I mean, it helps with getting the overall trajectory and the breakup events, and and we still have so many infrasound stations now that for everything from seismic stations now having infrasound to other military listening instruments that are out there. Right. A lot of that gives you very critical information for those breakup events and what it's doing in flight. I think the Doppler, mainly is just, it's incredible now that it tells you, these low pass sweeps, particularly from the local weather channels, they give you information about how much material really is making it, and maybe even some idea about how big the individual pieces are. I mean, if you had a large fragment in there, the Doppler's going to see it.
Right.
And so these are used somewhat religiously by the meteorite collecting community now, to really do everything from telling them where it's worth their time and effort to make these trips that they make very quickly off to these remote locations, down to when do we call it quits? They actually will make calculations of, well, we found a kilo of material. It may have been divided into 10 pieces, but the Doppler says that we should only expect a kilo of material, so I guess we're done.
Right.
We do have a question. Somebody asked, maybe the Trillion Sensor Initiative will catch something. I'm not sure what the Trillion Sensor Initiative is. I've not heard of that. No? Okay.
Nor have I.
Okay. I was going to ask you, Scott, so I don't know how long ago it was. It might have been several months ago. There was a ring camera video that was released of a place in Prince Edward Island, Canada, not too far from where I grew up, by the way. And it showed like an impact outside, just outside the patio of the house. I think you know what? Yeah, that was amazing.
Yeah, and so we got to see that sort of puff of dust, even in that case.
Yeah.
And I think that's, I wish that had been positioned a little bit differently too, so we had seen the actual point of impact. But you still got to see what was left. You got to see the dust, and so I think that's also that was important in kind of informing the speeds of this one that hit in Georgia in June, because that was a relatively small object too. There you hit, most of the object is intact, but it did hit brick, so there's a puff of dust from both the brick and the bolide. But then the one I showed you earlier, this is from the same collision here. Maybe that's something 3-4 times larger than the piece that went through the house. This one did what they mostly do, which is kind of came to rest harmlessly in somebody's backyard. That's probably in free fall. Right? That's traveling 100 meters per second or so when it hits, and very different than its cousin that probably was out on the leading edge after the breakup, still probably going 800 meters per second or so, and even being smaller, still did quite a bit of damage. If that had been going 800 meters per second when it hit the ground, I think we'd have a pretty decent little hole in the guy's backyard. But nothing huge, but at least maybe like the size of a bucket, and instead, it just landed kind of harmlessly in the grass.
Yeah. Now, one of the things people hear about this is when you attach an age or date to the meteorite itself. So maybe you can say a little bit about how do you even do that? Because some people, aren't. How do you date something that's billions of years old, type of thing?
Well, the age thing has been kind of an interesting subject with this one, and I've sort of got there's a lot of tension when people wanted to quote me as saying, "Oh, it's older than the Earth," and suddenly they slapped a number of years, and I never said, "Oh, it's this much older than the Earth." What they did is they took me saying it's older than the Earth. They went and looked up the latest sort of Google your Google your latest AI, and it slaps out some 4.5 something billion for the formation of Earth. And so, well, if this is older than, or if I could say this is 4.56 billion, well, how much older than that, AI, listed age of Earth was it? And it's like 0.02, so 20 million years. And that's why I kind of went out there. But I kind of went back and said, well, look, I mean, the chondrules here and the stuff this is made of, yeah, it's older than the Earth. I mean, that's kind of the whole point of studying them from a meteorite standpoint, right? Is they're the building blocks of the terrestrial planets, and that's why we want to, that information. It tells us about those early days of our own planet's existence. But then, of course, that material comes together, it heats up, so you really have a metamorphic age of that. Then if these are larger asteroids, they may take a while to cool down. So there's really a range of ages of material in these. But yeah, the oldest stuff is older than the Earth, and the youngest stuff is probably around the age of the formation of the terrestrial planets. And then they cool off very fast, and the larger planets cool off slower. So there's a whole smearing of ages if you wanted to pick anything out of there. But to your question for your audience about how you do this, well, if this had been the first L chondrite ever found, then we would take that into a lab. We would find some piece that we're comfortable crushing up. You would get different minerals out of here. Principally, if you can, it's great if you can get minerals like zircons that have a lot of uranium and lead in them.
Yep.
Because we know the isotopes of uranium and how it decays to lead very well. Very good radiometric clock, as we'd say, and we can and good assumptions about what the starting materials would have been at the beginning of the solar system, and so you can get a really accurate measurement of how long ago that radiometric decay started in the minerals in this rock, and you get an age, and that's kind of how it's done. Now, did anybody go and date these particular ones? No, no, because once you dated certain ones, at least common ones, then you go and you do the detailed geochemistry to tie this rock to a whole other group of rocks where we already have plenty of age data. And then, most ordinary chondrites, L's and H's and LL's, they're all presumably from different bodies, but they all have these ages of around 4.56 billion years ago.
Right.
Right. And if I remember, L's are, like you were saying, highly metamorphosed, but
Some
they
are.
still do have the chondrules, right? And it's the
They have a
chondrules.
range of of metamorphic grade.
Okay.
The nominal ones are kind of in 5, 6, and then some you might run into some 4s. You can run into some some that actually are right on the border of 3s. I mean, have beautiful chondrules preserved in abundance.
Okay.
But
I was wondering about that because you're 100% correct in talking about radiometric dating. You've got to take all that into account because what you're really dating is when things solidified.
well,
And
or it depends on where you are in the rock, right? I mean,
right,
if you're looking at the part that's really heavily metamorphosed, then yeah, you're getting some element of that heating down the line from when the original material came together. But if you're lucky enough to get some datable material in one of the chondrules or in some of the melts directly associated with those, then you're probably getting the actual age of the accumulation of those.
right.
Is there any hard, fast definition to the word primordial in this case? In the sense that at least everything, at least to some degree, whether it's a small degree or a large degree, has been altered since its formation, if you want to think of it in that terms.
Well, I mean, chondrules themselves, the little beads that the round things that chondrites take their name from. I mean, they themselves are not primordial because they were dust dust that had cooled out of the solar nebula,
Right.
and that dust then got energized, either hit. It's been proposed they may have been hit by giant static electricity discharges. Imagine lightning bolts jumping from the sun out past Pluto, and literally melting any little dust in its path. So you get little melt droplets then formed in the solar system. These may also have been, some of these may have been formed when larger impacts occurred. Once you got asteroids forming, they ran into each other. There were impact collisions that you had melt flying out from. Truth probably is that there are a number of ways you could get free melt out there that's going to form into spheres. So, that's almost a second generation or third generation material there at the beginning of our solar system anyway. When we really kind of in the solar system, when we start talking about primordial, well, that goalpost changes too. But we kind of think about those carbonaceous chondrites, the carbonaceous asteroids, and that were from deeper out in deeper, colder parts that were not even affected after they formed by the heat of the sun too much. But now inside of those we have pre-solar grains that if you get dates on if you're lucky enough to get any of that material that is datable, you can come up with radiometric arguments that some of those go back to 8.5 billion. And so they,
wow.
Those then, as we know, just from the chemical soup that our solar system is made up of, you can't get the elements we have from, without a one or more supernovas occurring and producing those heavier, the heavier Z elements higher Z and heavier mass elements. And so where'd that come from? Well, there, at least some star nearby our little corner of the solar system, or some star near our edge of the galaxy had to blow up, and in that process, you've got these grains of material that are out there. They're accumulating, and we're lucky enough to find them. So, is that primordial enough for people who want primordial for the solar system, things that predate our own solar system? Or do we, are we going to get to are we not going to be satisfied till we find things that even, from the generation of star formation before that, all the way back to the beginning of the galaxy? So your goalpost shifts depending on kind of what you're talking about. But for those of us working in the solar system, primordial for us is probably, the formation of the sun itself, which, estimated about 6 billion years or so.
Something like that. And then, given how fast we're moving around the Milky Way, I mean, we're going around about 4 times every 1 billion years. So we've gone around, about 18 times or so. So you never know what type of mixing or encounters that would lead to. Is there any, I never asked this ever, and I don't remember ever reading it anywhere, but is there any hint of sort of residual magnetic field from the early protoplanetary nebula, that pre-solar nebula that started things? I know we know like the sun's magnetic field and planets and stuff, but there's any evidence for that magnetic field in the disk of material itself?
Well, yeah, and there's certainly colleagues who look at the paleomagnetism in the meteorites. I mean, it's really important. This is why one of the many reasons that if you ever find a truly what's called an oriented meteorite, most of these objects come in and they tumble. Right? They're spinning out in orbit around the sun. They tumble in, and you get fusion crust, all the way around.
Yeah.
But occasionally, you get pieces that at least are oriented with regards to their travel through our atmosphere. Whether or not that really represents their encounter direction with us out of their orbit, maybe. But what else you're going to do? So there are people, when they have those that are oriented like that, they look very carefully at the paleomag and try to understand what that could be telling you. And even in unoriented ones, can find the remnant magnetization to at least know it was there.
Right.
Yeah.
We do have somebody asking about charge. Is there any indication of it having once been? I'm guessing they're asking if it's been a plasma or anything like that, which of course it would have been at one point. But is there any residual
dust grains? But yeah, you don't really see plasma, evidence of.
Right.
The record, other than pre-solar grains, the record of the really early stuff that is melting, those are far and few between. Ultimately, for ordinary chondrites anyway, we get these beautiful chondrules, and what happens to them, and whatever that moment in time was that you got these static discharges or impacts to produce these little melt spheres. They're that's one of the things that has been worked on for as long as I've been interested in planetary science, which is my entire life, and I'm in my early 50s. So there's not a time that I don't remember, even as a kid, looking up anything about planets and chondrules, and you'd have thought back then that, okay, well, by the time I'm 50, somebody's going to have a pretty concrete idea about how these chondrules formed, and the same hypotheses are out there now.
Right.
It's like you're a little bit further down the road and sort of say, well, it may be more this one or more that one, but still nobody's 100% sure.
Yeah, and I think in the 1990s when they started finding exoplanets, so planets around other stars, that people realized that there's this planet migration that can occur, so that you can dump some heavier elements into the outer atmosphere of the host star to build up its metallicity by doing that. But it wouldn't be just the planets themselves; they would migrate all this other material around as well. In fact, that would lead to a pseudo frictional type of environment where you're going to have a lot of the charge separation, and that gives rise to that static electricity that you were mentioning. Yeah.
I'm just trying to imagine what that would even look like. This great bolt going jagging through a protoplanetary disk.
Well, I can imagine you spent all this time, let's say in the distant future, going to some other star system just to be killed by lightning bolt.
A lightning bolt. What is essentially a lightning bolt.
Yeah.
Wow. Yeah, because is it bolts or is it some big diffuse cloud that suddenly just fries everything simultaneously?
Right.
It's like
Yeah, and
great fodder for science fiction.
Yeah, for sure. It's like a giant open circuit, right? And episodically sends a charge down the line or something, right?
The primordial Van de Graaff generator.
Yeah, exactly.
Let's see. We've got another question. Does the object's high speed interaction with our magnetic field affect the polarity of the meteorite? And I would think probably not, because it'd be just going too fast.
Yeah, I don't think there's any time for any adjustment on any meteorite coming in. Now, what does happen, and this gets over to what my primary field, which are the impacts. When you do have large impactors hit, or even airbursts up in the atmosphere, like Tunguska type things. We actually published a couple years ago evidence of probably a cometary body having an airburst over the Atacama Desert back maybe 10,000 years ago or so, and actually enough radiant energy hitting the ground and actually convection of material on the ground too to create glasses. You want to talk about screwing up a paleomag record? People are familiar with the notion of EMP blast, right?
Right.
The whole point is to screw up your magnetics, and so you cause a problem with the electronics and induce currents. Well, big impact events, they do actually have an effect on the magnetic fields, on the materials that are created out of that. If you're creating plasma by the collision, or you're creating, these vapor melt-rich environments and plumes, that is an entanglement that is really fascinating. And, there are lots of people who work on that problem.
Cool.
Yeah. Now, this is going to be silly, but I noticed the other day there was this video going around from China where it shows someone claims, I don't know if the Chinese government officially claimed this or not, but it shows like a fireball. They're claiming it's a meteorite coming through, or a meteor, and then you see a missile, I guess, coming up from the ground, intercepting head on. Did you see? And I'm like, number one, how did they know the right time and direction and everything that's coming in at, if it is a real meteor? And it certainly looks like it's more of a test of something, if it's even right or not, right? It could be certainly a fake thing. But
yeah, good luck on that. I mean, interdicting an inbound, a small meteor is, we're not doing that.
no, I don't think their technology is that far advanced.
Right. Yeah.
At that point, you'd probably easier to shoot it down with a powerful laser if you have the technology, right?
Right.
Yeah.
So, yeah.
But I mean, there's been the other thing I always wonder is misidentification can be an issue. When something happens, let's say it's an explosion somewhere caused by an impact, but you don't recognize that right away, and some governments, I hate to say it, may get itchy.
Well,
this kind of situation.
No, and this is the importance of somebody, my interest in the small objects, right? Something literally going through a house. I mean, they didn't know. I mean, I think the homeowner there, was knowledgeable enough to know what was going on. But imagine that you mistake that for somebody firing a high caliber weapon at you.
Mm-hmm.
Right? Your reaction is going to be different than recognizing, oh, did something from space hit? Right. And in a grander scale, this is, as I give a talk every year on the anniversary of the Copernicus event, which was yesterday. And the reason for that is, somebody might say, well, gee, this is a one-off thing. Why would you worry about something that made a 50-foot crater? I mean, a 50-foot crater is a 50-foot crater. For me, it's pretty big, right? But the issue is exactly what you said, is reckoning, you're not doing anything about a 1 to 2 meter size object. You're nothing you do. If you're going to get hit by it, it's a bad day. And if that hit a populated area, it would have been a very, very bad situation. But the worst part of it, I've told the story for years, is the worst part of it is not it lands in a populated area and takes out a city block, or at least a building or floors of a building, as something like that may have done. It would be the reaction to it, particularly in a post 9/11 world. Right? When this occurred in 2007, all the impact community was at a meeting in Montreal, and most of them, experts on these things, immediately told media, "Oh, that's a hoax," or "That's a military test." Even people on the ground we interviewed in Peru and Bolivia said, "Oh, we thought." Honestly, this is what they said. I tried to start an international incident. They said, we thought Chile was firing a weapon at us. We're like, you guys actually have tensions like that? And at that time, they said, yeah, we do. And we actually something we worry about. So if you didn't have a moment, if you didn't recognize pretty quickly what had happened, as I always say, the worst thing that somebody could do is turn around to an expert at that moment and say, have some government official somewhere turn around to an expert and say, what just happened? And I always tell students, what's the worst answer you can imagine that they give? And whatever that answer is, I usually say, no, the worst answer is, I don't know. Because now you're putting it in the hands of people who are interested in immediate response to do something.
Right.
And we need to know immediately. That was an actual natural event. That was a meteor. Calm down. Yeah. And that's extremely, that is a real risk that we face. I think, probably maybe greater than, we're going to get hit by the big one, or we're going to get hit by, something really small that really does cause a lot of damage. It's really something that causes a really minor amount of damage, but in a key place, and then there's an overreaction to it.
Right.
Yeah, I'm just thinking that we got to end now, but I was just thinking, Scott, it wasn't that long ago in Russia where we had that meteorite that came through and, the shock waves smashed out a lot of windows and buildings and so on. You imagine that happening now with what's going on in that part of the world. Would they be so inclined to think, well, it's not just a natural thing, there might be someone taking a shot at us?
Right.
Yeah, and I will share this with you cautiously. Is there was a lot of interesting. Everybody knows about Chelyabinsk that you mentioned there in Russia in 2013. Very few people, even in the community, know about Barkhouse. But I mean this was one that actually hit, that made a crater, real crater with shock materials and everything. And we had even though we got our papers out, we had a lot of very, very noticeable suppression of that in the media. And it was pretty obvious why, and we had people with the Department of Energy that worked with us on this, so we kind of had some insights. There was a real worry that you just had nature give you a blueprint for the correct size and entry angles and entry speeds to fire something from orbiting platforms and not be able to detect it immediately.
Right. Yeah.
Oh my.
And that was a really real issue.
Wow.
Turn it into a weapon.
Yeesh.
Yeah. That's unfortunate. Really is.
Well, I
Well,
think we're about out of time.
yes, and thank you very much, Scott, for
Thank
doing
you.
this. Really appreciate it. Definitely learned
Thank
a
you.
lot. Definitely learned a lot. So if you're out there watching this and you're interested in maybe getting involved in the kind of work that Scott does, one of the things you can do, of course, is go to higher education, such as the University of
North Dakota.
North Dakota. And we have both online courses and also on campus, and we're willing to talk to you if you come here and get you all set up and whatever interest you have.
Yep.
And make sure you're in the right program and in the right path. Now, our next podcast will be next Tuesday on September the 23rd. We always leave you with a quote at the end, and this quote is actually related, and it's by Lawrence Krauss, who's not a geologist, he's really a cosmologist, but he wrote back in December of 1986 in Scientific America. And here's the quote: "Of the 10,000 or so meteorites that have been collected and analyzed, 8 are particularly unusual. They are so unusual, in fact, that since 1979, some investigators have thought they might have originated not in asteroids, as most meteorites did, but on the surface of Mars."
Neat. The Martian meteorites.
Exactly.
Yep.
Okay, anyways, thanks you. If you like this podcast, don't forget to give us a thumbs up and subscribe if you haven't subscribed, and we'll see you next time. Thank you.
Thank you, folks.